Now it's time for me to introduce our next keynote speaker. So we have with us Professor Navin Kumar from IIT Ropar. Sir did his PhD in 2006 in mechanical engineering from Indian Institute of Technology, Delhi. His research area includes hard, bone and soft tissue mechanics, biomechanics, biomedical devices, finite element based modeling, smart structures and materials, fault diagnosis and condition monitoring, active vibration control. Sir is a professor in the Department of Mechanical Engineering at IIT Ropar. Prior to joining IIT, he was working as a research scientist at Stevens Institute of Technology, New Jersey, USA. He has completed his master's in mechanical engineering from IIT Kharagpur and PhD from IIT Delhi, as I already mentioned. Dr. Navin Kumar's research interests are related to vibration and noise, fault diagnosis, and condition monitoring, biomechanics of hard and soft tissues, biomedical instrumentation, smart structures, and material. I kindly invite Professor Navin Kumar, sir, to please take the dais or podium and give his insights. Thank you so much, sir.
Here, particularly the Nirma, who are organizing this conference. We know that organizing a conference is like a daughter marriage. So I can see some of you are from day and night organizing the things, which is really, I appreciate your efforts, and you have very beautiful campus here. Today I am taking a walk in the morning and I can see the new birds every day. Also, I also thank the ICMP team here. My friend Swadesh is here. Anand, we are batchmate. You know, we have the Kunwa, you know. So, you know, Dr. Swadesh is Indian IES. He has left the IES and he joined there. In fact, we have lost a IIT faculty. Here, I have called when I have joined IIT. I called him, but he was not ready to join IIT because he is earning crores of crores, which we cannot give him. So, which is I got to know after that once. Okay, so I will. Dr. Anand has initiated a very good topic. He talked about the machines. I also used to work in same topic, condition monitoring, but I work now in different machine. I work in the human machine now. So I will connect. You see, we are also have the machine inside. And it is with us only. So we give the example of the gear like Dr. Anand is giving, or beam or plate. But we never give our examples, which we all of us has. So this area I have started in about 13, 14 years back. When I came back from US, I was working there. So this is my lab. My lab's name is Hasotum Lab, which is acronyms of Hard and Soft Tissue Mechanics Lab. My students always remain happy, but you can ask them whether they are happy or.
One thing I would like to tell those who join this lab, they get married immediately.
So my lab is also a marriage bureau, right? Okay, so this is the, we are located near to Chandigarh, and about 35 kilometers away from Chandigarh. This is beautiful campus, I can say, most beautiful IIT among the all 23, 24 IITs. We can say that, we can have that. Our pillars are cost now 24 crores. These pillars are, this is actually Harappan civilizations dedicated to, you can see that incarnation of here. A lot of stones are there. So this place was Harappan civilization place. So we have dedicated this pillar for them. And then on the top is this scientific means we are doing the scientific research. So these are the chemical structures. We are doing good. We are among the international. We are 68 Asian universities as per the Times. And IRF we are 22. So you see here, this is my first slide, which I also teach the orthopedic biomechanics in IIT. So this is the first slide. Those who are from the mechanical side, they can see this now. You see, we talk about the lot of joints. We talk about the hinge joints. We talk about the ball and socket joints. We talk about the saddle joints. But these all joints, we talk about the pivot joints. These all joints are with us. We are always with us. But we never give the examples to our students when we teach them. So it is not the fault of the student. In fact, it's the fault of us, the teachers, which never give those examples because they are with us only. So you see, we are using these hinges for all the doors. They have the hinges. All these locks, they are the pivot joints. This is ball and socket joints. All the flush system has this. But we never have those things. So my emphasis, please come in that domain also. This domain is very big domain. A lot of people are needed. A lot of research is needed. Now coming to forces. We talk about the compressive, tensile, shear. These all the forces are there on the bone. So this is a femur bone, the longest bone. Now these forces also come together. So it's a more complex phenomena than in general machines which we do. Then here, if you see that this is we taught in the 5th or 6th class, the levers example, class 1 lever, class 2. There we give this example of our hand or our neck, but after that, nothing, no bios related thing. In fact, we have the allergy to each other. The bio people have the allergy to the math and math people has the allergy to the bio. To the extent they don't want to talk even. And that's the reason. That's the irony is that in our country we make the medical colleges and engineering college, IITs and AIMS. That's why we have segregated these two sciences, and that's why people are interface is not there. So I will talk about a lot of interface, what is happening. So I will start with some of the interesting thing, which is I think this general. My initial slides will be general, particularly for BTech or master students. There is no such research in there, but it make you feel that this area is really interesting to see that how, particularly our nature, in particular the insect, the animals, how they work, how they use the science, I will talk about. Now you see, I will talk about the spider web, wasp, mosquitoes, how they do that. So if we talk about the spider web, you see that you may feel that it's making, but it's not. It's have a lot of scientific input. First of all, it's a wonderful architect, combination of geometry and mechanics, and a lot of structural integrity, a lot of kinetic energy absorption, a lot of science is involved, which we'll talk about. So I'm also from vibration side. So you see how the vibrations are also coming in the biomechanics. I will show that. So when she is making its web, it is like this. It is. So this is the very slow speed she is making a web. So you can see how meticulously she is making these parallel thread. You see, these are all parallel. You can see that, and these claws where she is releasing this, they are also a microstructure. And then you see this is a slow speed. Now the actual speed is this. This is the actual speed. She is so quickly making it, right? But making is another aspect. But what are the quality it has? So what we have done, this is our BTech student final year project it was. So what we have done is, we have collected this web. We have taken a glass slide. We have taken it near to web, and the web is stick on that, and we have collected it. This make our sample, right? Then what we have done is, we have tried to see in the electron microscope or SEM. So there are two type of thread. It has a radial thread, which is this one, and the spiral thread. The radial threads are thicker. They are more thicker, and the spiral are thinner. Why they are thicker and why they are thinner? They have the specific quality. That's why she is doing this. So the radial threads are like the framework. If you're making a building, you are making the beams and pillars. So these radial threads are the beams and pillars, right? The structure actually. And these spirals are the walls. They are completing it. But it is the spiral is near about 80% of the total thread, and the radial is near about 15% to 20% of the total thread. The radial threads are thicker, the spiral threads are thinner, but they have the gum points. So when she is weaving it, she spread the gums at different places. You can see these are the gum points. The gum points are more on the spiral thread because the probability of the striking the insect is more on the spider because this is more on number. That's why she is keeping this, spreading the gum on these threads so that when insect come, it is stick on this gum. So what we have done is, we have done very simple. We have done, taken the on this glass slide and done the indentation, right? So we have the indentation tool. So here what we are measuring the load and penetration depth, how much depth our tool has gone inside the thread, right? So here you can see the indented specimen here. So much of depth it has gone. So when we have noticed that in radial thread, the depth of penetration is about 25 nanometer, whereas in the spiral thread it is too much, about 110 nanometer, right? It means our radial thread, the indentation is depth is higher than the radial thread. Means the radial thread is little bit stronger than the spiral thread. So because here it is like a structure, she keep that the radial thread is stronger than the spiral thread. Now what we have done, we have we try to see the vibration and try to see that's how much damping in this structure. So structure damping is very important. So now you see the how we are using the vibration here. So what we have done, we have put a laser vibrometer here. We have put a laser spot here. You can measure the vibration by without contacting the structure. So we got this the response, the time response which Dr. Anand has shown. So same response we got. What we have done is we try to find out the damping. So you can, if those who are from the mechanical side, they have studied in third year or fourth year vibration course that you can find out the damping by logarithmic decrement method, which is the I have used here. So we have tried to find out the damping of a spiral thread and the radial thread by using this logarithmic decrement curve method, right? So here once we found out, so this is a spiral thread and this is a radial thread. So the structure which is settled down quickly has more damping. So from here you can see the vibrations are settled down within 0.1 second, whereas the radial thread vibrations are taking time. So the damping of the structure which is settling down quickly has more damping. So you can see that here the spiral thread has more damping than the radial thread. It means the spiral thread more damping than the radial thread, whereas the radial thread has more strength than the spiral thread. You see how beautifully she is making, because here these structures, the spiral thread, more damping, so that the probability of the insect, when insects are coming at having a lot of kinetic energy, it needs a lot of damping to absorb that kinetic energy. That's why radial spiral thread has a lot of damping in it, in the structure, so that when a insect is striking at those surfaces, it can absorb the energy and quickly that insect will not break the web and stuck there. And one more study we have done. So that's the work we have done. We have published this work in very good journal paper, say 4 impact factor journal. These are my BTech students. They all has gone out now. But this is my postdoc fellow. So you see, BTech student also can do very good work if you give very simple work to them. This is one of them. Then a lot of media has covered our this such type of work. So this is Times of India News, and then you see now these spiders are cannot they are blind. In fact, some of these spiders are blinds, but they can hear the vibration signal. So how they do it, you can see that. So this is in our lab, we have make a frame, and by chance a spider make a web there. So you see And we try to see that how this spider is responding or once the prey is come, right? So you can see, and she used to sit in the middle. So she is sitting in the middle, the spider is sitting in the middle, and we try to put a insect in the web. So here you can see, so once we put a insect, she quickly come up and catch the, you see here, she has catch the insect. Beautiful thing is that why we have done this experiment, we try to see that how she get the signal that insect is here. She followed this path only. She has not followed this path and come back here because she cannot see. But she is getting the vibration signal or get transmitted from this insect to the web, to the spider who is sitting in the middle, and she has captured those signals. So you see the use of vibrations. Also nature using it like anything. That's why when you go in the woods or in the jungles, the insect get your foot vibrations and they realize that somebody is coming. Then surprisingly we have put the dead insect. Dead insect, she has not responded. I think the flickering, once the insect is strike in the web, the flickering, she also see that whether the flickering message is coming or not, the signals are coming or not, but we don't know why she has not responded on the dead insect. So what we have done, we try to see how these signals get transmitted. Because for signal processing and development of sensors, these studies is very important. So again, we try to see that how this signal is get transmitted, whether through this channel or through this channel or through the radial thread or through the spiral thread, we try to see. So on each spot we keep this, we are measuring this vibration level on each spot and try to see that how these vibration signals are get transmitted to the spider. So we try to, there is a transmissibility chapter also in the vibration, those who are study the vibration. We try to see that how this vibration signal get transmitted through different zones, through the spiral thread and through the radial thread. And we have shown that they are having some path. The shortest path she is following, which these signals are coming, and that's the how the vibration signal get transmitted. This again work has been published in Philosophical Transaction Part A, which is the oldest journal in the English-speaking history. In this journal, Newton has published his work. Now coming to another very interesting work, you see how the wasp and honeybees are biting you. What is the channels? They have wonderful mechanisms how they are inserting the venom in your. So this is the honeybee. The back, this is known as stinger, which is hardly 1.5 mm to 2 mm. So if you, they have the thread from the prey, so they take out this stinger. You see, she is taking out, and then they insert into the prey. So this is the stinger. You see. Now, what we have done, we have taken out this stinger, which is hardly 1.5 mm to 2 mm, and we have taken the CT scan of it. So if you do the CT scan of it, we have all this system in our lab. We have a lot of very big funded lab, funded by ICMR, DBT. So if you see that the internal structure of these stinger, it is not a cylindrical structure. It is cylindrical structure, but in two halves, the lower half and the upper half. The lower half has the channels, which is, we are saying, the lancets. On these channels, the upper half slide. So when she bites, what is happening? She is doing, she is sliding the upper half. She is sliding the upper half so that the negative pressure develop here. Here is a sac or a bag of venom, which is located here. So full venom bag is located here. When she bites, she is sliding the upper surface. A negative pressure generated here. The fluid or the venom start flowing through this microchannel and it's coming out through this orifice, the end. So this, she is just sliding, the venom start flowing and it's inserted in the prey. So you see there is a natural pump. She is using the negative pressure to insert this venom in the prey. Similarly, what is the biologist has reported that when she is biting, she is making some certain angle so that optimal angle should remain, so that this stinger should not be failed. We were thought that maybe they are just saying that, but we have done that this finite element analysis. We try to see that at what angle she keep from the vertical. When she bite, we have the videos. When she bites, she's little bit adjust this angle. So don't forget that they are very smart. In fact, smarter than the human. They are keeping certain angle, and why they are keeping? Because the stresses otherwise this stinger may fail. So maximum stresses are coming at those angles. So we have shown that you see between this plus minus 20 degree, these maximum stresses are coming. That's why she's keeping that stinger at that angle so that it should not fail. Based on that, we have filed a patent. We are saying that we can have this the syringe micro needles, which has the medicine infilled, and then you can just slide the upper portion. You can insert the medicine into the patient. In fact, this mechanism is not painful. The venom is making the pain, which is a poison, which is making the pain. The mechanism is not making the pain. So we have filed this patent, and we are saying we can design such type of needle. So we got this publication again, and very good journal. Now, very interesting work I will show you. That what the lesson painless, how the mosquitoes is biting you painlessly. So they have a beautiful arrangement, which is I was also surprised. They have some numbing agent. This is people are saying, but we have not investigated. When they bite, they are making this their proboscis by certain vibration. Again, vibration come in the picture. Low frequency vibration, and they have some anticoagulant agent, which I cannot verify. These are all cartoons made by my students. Very good cartoonist. In fact, he was cartoonist. He was gone to. It was again a BTech student. He has gone to Iowa State and he has done the PhD from there now. So this is the again his this is his drawing. So this is a proboscis which this mosquito insert. So if you see here, this is also known as the upper portion is also known as the labrum. So this labrum go inside and it's bite you and take out the blood because it's a hollow structure. So now you see how beautifully she is, or the mosquito is doing. So the mosquito is searching your blood vessel because they have the CO2 sensors. They know that where is the blood vessels. Now they Dr. Shodhe are laughing. Again, we are surprised to see those things. So it's inside now. So inside this proboscis is inside. You see, it's search the blood vessels. Now it is inserting it and it's take out the blood. So you see how smart they are. So you see it has inserted. It's find out the located. Now it's taken out the blood. You see. So so it is so interesting. You see. Now what we have done, we have taken out, sacrificed a lot of mosquitoes, and we have taken out their labrum, and we have done those studies. So what we have done is, again, we have this is structure is near 150 micrometer full structure. We have put near about 100 indentation on this and try to see how this property vary. We want to see how this beauty of this proboscis, so that without pain it penetrate. Why? How this happening? So we want to see that. So to the surprise, and we have also done this indentation in the dynamic mode. We have the instrument which can do this static mode and dynamic mode. So then we have done this on the 100 locations, the indentation, and then we have find out the modulus of hardness at those locations, and we have plotted it, mapped it on those locations. So here you can say the summary of the modulus on this surface. So this is a tip, this is a proximal end, this is known as distal end. Now we were surprised to see that the tip is not so hard, or so modulus is not so high, but it is higher than the our upper dermis modulus. It is higher than the upper dermis modulus than the but here it is harder. So we were surprised. We have repeated. We were expecting the tip will be harder so that it can insert, but it's not the case. So then we have tried to see the mechanics. What is happening is, you see, it is bulging here, bulging or corrugated. It is folded structure here. So if you have seen that tin shades are also corrugated structure, right? What the God has made it, they have made like corrugation here, corrugation here. Corrugation always give you the more stiffness. It increases the stiffness. That's why tin shades are corrugated so that it should not bend. Similarly here, the end surfaces are corrugated. It is more stiffer than here, so that when it's inserting this in the upper dermis, it should not bend. That's the reason. That's why these ends are little bit harder, higher, more modulus than this tip, and that's the mechanism. That's how the mosquito is, and then she is also wearing its modulus, because the tip is vibrating within 10 hertz. We have shown higher frequency, but it's not the case. Within 10 hertz, it is adjusting its modulus. You know, viscoelastic materials are variable modulus or hardness depending on the frequency. It can vary. So that same property is using. And again, we got a very good paper, and based on that, we file a patent that the needle, when we are taking out the blood, can be this, when we mimic the nature, so that the patient cannot have so much pain, which is the regular needles are there. I have another. This is my main work now. This all were my byproduct. We work in the human subjects. We work on a lot of bone and tissues. We try to see that how the bone and tissue qualities are degrading. We are the pioneer in all over the world that we have shown that type 2 diabetes is deteriorating the bone. Our paper is so much cited now. You see, most of us has the family members who are suffering with the diabetes. You may have seen they have first renal failure, the kidney failure, then retinopathy, the eyes problems, then other organ problems. So in fact, they are also affecting the bone also. That we have shown in this study. So why this study is important, you see. This is the population pyramid, which is, we have about 31% older people at present. But in 2050, we will have 46% older people. The same condition is prevail here in US. We have near 40, they have near 48%. So what I'm trying to say that this area is very promising area. In future, our condition will be also same, but our infrastructure is not good. Our hospitals not so equipped. We have very high population. So it will be a pandemic for our country. They are suffering also, but our country at present is a younger country, but no longer it will be a younger country. We will have the older people. So this area is very important to work on these skeleton problems. We are diabetic capital, also known as, other than the African countries and China, we are the diabetes. So diabetes is affecting the bone. And the new terms which has come up is the bone quality. So our group also defined this term. So earlier the issue is that those who has done or who has gone for some bone issue related issue, the clinician has only one tool which is known as DEXA. It's a X-ray based imaging techniques. They do the DEXA and find the bone mineral density. Bone mineral density, one of the indicator that your bone is deteriorating. But in some of the pathological cases, particularly type 2 diabetes, these DEXA do not give the correct reading. That's all over the world. Clinicians and surgeons agree on that. They say that in some of the pathological condition, DEXA is not giving the correct, but they do not have any other tool. So then we have worked on it. We have say if you also measure these three parameters, the structural parameters, the material parameters, and the chemical parameter of the bone, you get the clear picture. which we have shown that if you have these other parameter, you can get the clear quality, bone quality. Now, so that's our thing. You see, what is the problem here? So these are all our CT scan images. These are all my lab work. You can see there are 3 patients. We have thousands of patients with us. We have thousands of sample of bone with us. So here, these are the 3 patients, a female. So this is the Ex-IES score, which is I was talking about, the T score. You see, these patients have both the same T score. If T score minus 2.5, it's a osteoporosis. If it is minus 2, it's a osteomalacia, before the stage of osteoporosis. Now, minus 2.2 indicate these both bone are same. For clinicians, they both are same. They give the same treatment. They give the same medication for these 2 patients because they do not have any other tool to measure the bone quality. Similarly, here you can see this is a severe case. But when we have measured, taking the CT scan of these patients, and we measure the modulus, the elastic modulus of this bone, you see we find surprisingly very high modulus of this patient in comparison to this patient. It means these 2 patients are entirely different. You cannot give the same medication. This patient needs some medication. This patient do not need some medication. We have hundreds of such examples with us that because clinicians do not have any tool, the medication was not proper, was happening. So we come out these 3 parameters which I have talked, and then we have come out that if you include these parameters, you can. So we have a lot of samples. How we collect the sample? When these patients go for hip surgery, the surgeon take out this femur head, they throw in the dustbin, we collect them. We have all the ethical approval, and we do a lot of analysis, lot of tools we have, chemical, mechanical, and structural analysis. You can see these are the structural images. So our bone is of this type. Yesterday, Professor Ramamurthy was also talking about the porosity and mimicking from the nature. So we have also we are also working on the 3D printing of the metal foam by mimicking the bone. But here you can see these are the CT scan image we have taken from our CT. And we have also done the indentation, compression, and ultimately we are coming, this is a DST funded project. It's a very heavy funded project. We are developing a tool for the clinicians so that other than the DEXA, if we include these 3 property, the clinician may have the correct indication. Now you may say that you need to take out the bone. But we have developed a device which is in vivo device. There is no need to take out the bone. We have the small handheld device which can be used. So again, this is a funded project from the. So here we have developed a tool which you can do this the assessment of the bone in vivo. There is like pain, like you are inserting the injection. So this is a device we have developed. Again, this is under development. We have developed the prototype. I will quickly, because I know my time is about to over. But another thing is that there is we are developing a extendable implant. Just a minute. We are developing a you were talking about the implant, so that's why I put this slide. We are developing a externally actuated implant. Why it is needed? You see, some of the cases you may have seen the scoliosis patient, those who has their spine is bent. So if you know Ira Sehgal, who is the 2014 IIS topper, she was the topper. She was having the scoliosis. Usain Bolt also has the scoliosis, partial scoliosis. So here, these patients, you see this pathological conditions in the birth, it is not there. From when the child is 8-year-old, it is started showing this signal. And by 13, 14 years, the spine is bent in any plane, in the horizontal plane or in the other axis. So what surgeons do, they do 4 or 5 surgeries. Why they have to do? They put the implant so that they can bring it straight. This spine bring it straight. But because these children bone are growing, so they have to change the implant make the higher size implant or bigger implant so that they can cater those growing bones. So problem is that these children has to go near forced surgery. They have to open this, take out the old implant, put a new implant because bone has grown. So we are developing a externally actuated implant, which is, so you can see some of the children's, and this very so many patients are there. If you talk about the Asia, about 15 million patients are there. If you talk about the Africa, North America, so many patients are there. So some certain methodology, I am not going it. So we are developing a growing rod which is magnetically actuated from the external. This is again in development. We file a patent, but I am not showing full details. But we are developing this. This is a magnetic rod which is externally actuated, so that the surgeon don't have to every time open this the open surgery. They can do external actuation so that this rod can be increased, the length can be increased. This again, we have developed a pelvic implant. Again, we are working with the lot of hospitals. I will in the end I will show you. So here we are testing the fatigue life of this new pelvic implant. So here we have this fatigue testing. We have the high-speed cameras. We are doing the online. You can see the strain development. So here, this is the new implant which is we have patented, but again I cannot show you. So here these are the during the loading, we are seeing how much strains are coming on this pelvic bone. I have put these slides for you particularly so that then we are doing a lot of implant modification. Some industries come to us, so we are having the CT scan and we try to see that how they affect the bone. We do the finite element modeling. We are also doing the implant testing. Quickly, I am showing these slides. And then these tibia plates, we are doing the fatigue testing of these plates. Some companies come to us and try to see that how this. We have developed a pelvic screw. We have this US patent also. So there is a pelvic screw in the particularly in the neck region. It is one of the surgeon in PGI Chandigarh has requirements. So we have changed this thread style. We have 3 different thread style of the screw, and we have done that. Once you develop a new screw, you have to do all this pull-out test and all those things. We have done. We got very good results. Again, so anyway, another we have working on the necrosis. There is a problem, particularly those from the COVID time. They take the steroid. Because of the steroid, a lot of bone issues are coming up. So avascular necrosis, the case where in the bone, the blood vessels are dried up. So the surgeons are putting the implant, but our group in one of the surgeon who is putting these cements along with these implants, they try to see that how the cement is affecting. So we are doing this testing as well as some modeling. So these are some of the results. Very good work we have done. We try to see this, can we detect the diabetes through the nail. So we have done a lot of tests and we have shown the community that nail also has a lot of information, our tissue, because this is our tissue. And if you test those nails, there is no need to do this blood sampling. You can get those. So that's again we have published this paper. And then you see our bone is viscoelastic material. They behave differently at higher strain. So this is a DRDO funded project, which we are trying to see that once the blast is happening, how the bones properties are changing under high strain conditions. So you see, high strain behavior is this than the low strain behavior. I am talking about the when strain is varying about 10 to power 1000 of strain rate. I am talking about in comparison to say 0.1 strain rate. So we have developed, we have this Hopkinson bar, high strain deformation bar. We have developed this bar. We have done a lot of study. We also work with the plastic surgeon. We try to see that how skin properties are changing. Skin also again a very wonderful tissue which is covering it's the largest tissue in our body. They have these fibers like composite structure. They have this collagen, the protein. So we try to see that how the collagen behave inside this skin. So we developing again device. This is funded by the Procter and Gamble. They want to see that how the cosmetic affecting our skin. So nowadays there will be a designer cosmetic. So we are proposing them, you can put some of our machines, they can give you the quality of the skin quality, and then based on this, you can suggest the cosmetics. And then how the diabetes is affecting the skin, we have done this. So we have published this in Acta Biomaterial, a very good journal paper, about 10 impact factor. These are our collaborators, a lot of surgeons working us. I'm thankful to all of them, all the hospitals, particularly PGI, AIMS Delhi, AIMS Rishikesh, AIMS Bhubaneswar, a lot of places we have. Recently we have in South, some of the hospital, Ganga Hospital in Coimbatore, we are working with them now. These are my international collaborators, a lot of people we have published, a lot of paper with them, we have joined project with them. Some of my students already working in those labs. These are my big group. I have 15 students has graduated, PhD student. At present I am guiding 15 students. I have a big group, my postdoc fellow, my staff, and this is my funding agency. I have near about 7.5 crores of funding at present. They have funded a lot. I am thankful to all. Thank you, thank you, thank you. Any questions?
Recently in Gujarat, BJ Medical College, where the spine surgery, the patient was having a